We're gonna get going here. Ladies and gentlemen, today is the last class until the break, and I had a bunch of material to cover for this class of three different sorts. Thanks. Good call. Three different sorts. Sort one, responsive to a question from last time. How do you take vectors of these monads, try or option, and render them into some representation for the results? So last time we saw that there could be a very nice syntax. We could perform this task of sort of successively taking values and processing them using calls to Flatmap, all the way down to the last, which is a map. But we saw that in Scala there was a nicer syntax yet involving what are called four comprehensions, which looks something like this. And I didn't have time to cover all aspects, but we saw fundamentally that we could write out a series of expressions that operate with monads using try, option. And the key advantage of this is that even though the expressions over here might be defined in terms of try or option, things like this, or things like this, where we have options coming in here, we can refer to these values x1, x2, x3 as if they hold the contents of those monads, the things contained by the monads, and yields an expression that involves those quantities. So this is going to yield a value. That's what yield does. It tells what value to yield. And this value, involving v1, v2, v3, v4, is phrased in terms of the values inside these monads. And if anything goes wrong along here, that, what happens? Well, it's short-circuited. We leave, and we get if it's a try-monad, we get a failure as a result. It passes along whatever failure that occurred as the result here. And if what happened is that an option value didn't work out, if it had none, we'll get a none for the whole thing. Okay? So I give a bunch of examples of this. It's a very nice syntax, and sometimes the examples we looked at were very simple in the sense that you're doing successive reads or something. Often what we have is processing along the way that's fairly involved. So we'll start with some value that's a monad, and then we'll process it in some way. In this case, we start with the URL, and then we try to read from that URL, and then we try to find the first occurrence of a certain term in that URL, and either of those latter two steps could fail. Maybe the term doesn't exist in the URL. Maybe the URL can't be read. Maybe it's an invalid URL or the site can't be reached. And if either of those cases occur, we'll get back a result which indicates that there's been a failure and gives us the reason for that. Nice basic idea, and we can use this sort of syntax to kind of clean up how we express those things. We almost write it as if we're not operating in terms of try values or option values, but in terms of the values contained therein, and it takes care of handling the failures, etc. This turns into, behind the scenes, calls to Flatmap, and map. That's what this turns into. The Scala compiler turns it into that. But it's a nice syntax. And we're going to come back to this issue of a for comprehension, where we loop over things, in fact, in a separate context, and we yield expressions there after the break. And we'll see how it compares with Python's comprehensions too. which are powerful tools that have some elements of what you get in Scala, but are somewhat more impoverished. Okay, so ladies and gentlemen, just to remind us of this, we before that we had seen how with streams we can have values that in fact refer to whole computations. This value holds a stream, but that stream has within it, it knows how to perform a computation. So if we ask for additional values, it will give us that. That too is a monad, as it turns out. But today we have some very pragmatic goals. The first is, I got a question last time. Suppose I have not just a discrete set of particular values, which can be trie monads or option monads or other types, but suppose I have a whole collection of things and I want to operate on them, a whole collection of tries or a whole collection of options. How can I use the tools that functional programming offers to handle these situations? And so I'm going to give a bunch of examples without dwelling a lot on any one of them, because we have two other queries, and in fact bigger queries this morning. So option one here, we start with a set of URLs. And here, we're going to map those URLs to the contents of the pages with the proviso that if the page can't be reached, if we have a fake URL, we get a what? We get a failure, which yields if you have a try and you convert it to a two option, success, which holds a value, turns into sum of that value, SOME of that value, a monad that holds that value, and a failure turns into a none, N-O-N-E, not N-U-N. Okay, so ladies and gentlemen, having done that, we get a set of strings out which basically include the sum for the strings which existed and none for others. And if we want to total them up, we could do that in a number of ways. We could filter those that are defined. So in other words, strip out the nones, only take those that are sums, and we could get them, and we could take the size of each and sum it up, for example. And another way we could do it is actually with a for comprehension. So we loop over these, and for each we get a page string, and that page string is in fact wrapped in a option monad, and then we yield the sort of the size of the page string, and we sum up the results. And this whole thing is in parentheses because this whole thing yields in fact a sequence of sizes, and we sum them. I don't have time to go over this, but we'll come back to that after the break. But let me show you a couple other examples. Okay, so here we saw last time we had some rand-ins, so we had quotients, and some of these rand-ins could be 0, in which case the quotients could include things that have errors in them, failures, right? We try dividing by 0, bad things happen. Mm-hmm. Yeah, so here, if we want to extract the errors, for example, we could take these quotients. One way to do it is to filter whether they're failed, and if so, process the exception, get the message associated with the exception, and then in fact render that into a set of strings. So this map here with the case will be covering what's going on there later in the lecture. But fundamentally, this turns into a try, which contains a message, and it's going to be a try that succeeds because we know that this is going to handle all cases of failures. And then we get the value of that and we turn it into a string. Getting the value of a try that has succeeded, a success, yields the value inside the success. So here we extract the errors as a vector of strings. But here, I provide different ways of basically taking the other values that were successful and turning them into and summing them up. So we can reduce these tries using get or else to treat the ones that are errors as zeros is one possibility. Otherwise, an alternative is we could filter to only include the successes, get the values in those successes, and reduce accordingly. Alternatively, we could map get or else over the values, treating 0 for the ones that failed and reduce accordingly. Alternatively, we could use, and this is a pretty nifty thing you get with Scala, you could use collect, which provides a partial function. It's kind of like a combination of filter and map at the same time. It only maps those that match certain predicates. And this basically says if this is a success, then we extract the value, and if it's a try, don't worry about it. And so it will only collect this for the successes, and this is the value inside the success. We'll come back to the syntax later in the lecture, and we sum up those appropriate values. Collect takes a partial function, a function that for some values is defined, namely the successes, and for others it's not defined, and those are just left out. Those are filtered out. So this does kind of a filter and a map all at once. Okay? So these are some examples of how we might process the values. And in your assignment 2, I'm going to ask a way that you might take a vector of options and turn it into an option of a vector. That will be for you to give me, not for me to give you. Okay? Right. I think I'll come back to these points later. Just be aware that we have something fairly special going on here, where we have functions that operate on values, and ints, doubles, and we can lift those functions. We can take those functions and have them operate on tries of ints or tries of doubles. We can have them operate on option of ints or option of doubles using map and Flatmap, in fact. We can lift them to operate on whole vectors in a way, say for element-wise addition, by using map on a vector. So we have a way of going from addition of ints to addition of vectors of ints by applying a map with a plus. We don't have to define a special method for vectors to add them up here. We can simply say map of this operation on individual elements. There's something significant about that, and we'll try to come back to that point at a later lecture. We don't have to define lots of special purpose functions for bigger collections. We can take the functions we're used to and apply them to those broader collections in a very straightforward way using things like map, reduce, filter, etc. Okay, I'm going to save these comments.